Hello everyone, welcome back. In this part of our series on cryptography and our Capture the Flag competitions at Ferris State University, we're going to talk about hashing. I'm Dr. Jerry Emmerich from Ferris State University's Information Security and Intelligence program, and let's get to it. So hashing is a special form of cryptography, but it's different than what we've talked about prior. Where it's a unidirectional, it's a single directional form of cryptography where we take plain text and we run it through the cryptographic algorithm, in this particular case a hash function, and we receive not really ciphertext but what's called a signature, some character output that is a unique fingerprint, if you will, in the form of characters that represents the input. And one of the characteristics of hashing is that you can't take that fingerprint, that ciphertext output, if you will, over here, this hash text, and run it back through a decryption algorithm to determine what the plain text was. In fact, it's just the opposite. You should never be able to do that. The hash function is insecure if you're able to do that. Okay, so it's one direction. We go from plain text to this hash text, or signature, if you will, and that uniquely represents what the plain text is. Okay, so forms of a hashing function that we use. Remember when we talked about symmetric and asymmetric cryptography, we had RSA was a popular form of asymmetric, AES was a popular form of symmetric in terms of the cipher or the cryptographic algorithm. When we hash data or plain text, some very popular forms of that are MD5, which is older now but still used quite a bit, and then various versions of SHA hashes are two very popular ones, and we'll take a look at that. So again, it's very important to understand the principles or characteristics of hashing. Okay, the input can be any size. Okay, it can be a single character, this plain text, or it could be the entire hard drive, entire storage system of a computer. Okay, that input, no matter how big it is run, executed through a hash function, MD5 or some version of SHA, for example, and what is outputted is this signature. Okay, the signature is some series of characters and numbers, and it's always the same length. It's always the same, that output is always the same length. Okay, and the length of that output really depends on which hash algorithm that you use. Now, this is a reliable process in the sense that if I take the same input, the same series of characters of the entire hard drive of a computer, okay, assuming it hasn't changed, and run it through the same hash algorithm, I always get the same signature. Okay, and again, that the hash function, you cannot take the hash text and determine what the plain text was by running it back through the hash algorithm. It's one direction. All right. So what are some uses for this? Well, one of the things we teach at Ferris State University is digital forensics. So the purpose of this video is not really to get into the digital forensics career, but it's essentially someone who works aside law enforcement or perhaps internally to an organization to investigate and process digital evidence that exists on some computing system. All right, and one of the things that a digital forensics investigator does is they make a copy of the digital evidence. So if they obtain a phone or a laptop from a crime scene under a warrant working aside law enforcement, they bring that back to their lab, and one of the first things they do is make an exact duplicate copy of that device's data onto some other storage device so as to preserve the original evidence and not alter it. Well, one thing that a digital forensic investigator needs to do is to prove that the copy of the original evidence is an exact copy. Well, if we're copying a computer that has multiple terabytes of data on it, we we can't do that manually, that verification that they're an exact copy, but we can use a hash algorithm. We can take the original evidence and run that through a SHA or MD5 hash and get a fingerprint, or a signature as we call it, in the form of characters or letters, and then we can do the same thing with the copy. We run that through the same hash algorithm and we get a fingerprint, or a series of characters and letters that represent a fingerprint. And if the two fingerprints match, then we know we have an exact copy. If they don't match, then we have a problem where we missed something in the copy, or something was altered during the copy. So we then have to kind of start over with our copying of that original evidence. Okay, so it's very important, and there are certainly other uses for hashes. One way that you might see it is if you're downloading a file from the internet. You're downloading a music file, let's say, from a website. Oftentimes you'll see that there's a hash signature that's given, that is displayed right next to the file name. Well, that is the fingerprint for that music file, let's say, that you're downloading from a website. Once you download that file, you could then run that hash algorithm on your local computer against that downloaded file and compare the fingerprint that is produced from that hash function to what was on the website. And if they match, then you know the entire file was copied and was not altered as it moved from the website down to your computer. So it's kind of a safety mechanism, and also just a form of verification that the file either wasn't altered maliciously, or that something didn't partially fail during the download and that you did receive the entire file. All right, let's take a look at an example of some hash algorithms. All right, so here we are at a website called onlinemd5.com. All right, and there are kind of two tools here at this website. One allows us to choose a file and then a hash algorithm, and it will tell us what the hash signature is of that file. All right, we can also just enter some text. Okay, so I'll enter secret password. Okay, and here I'm selecting the MD5 hash algorithm, and this is the unique MD5 fingerprint or signature for the plain text input secret password. Now watch this down here. This currently ends in 7B and begins with A5, just as a way to kind of see the change. If I change a single character here, this signature completely changes. Okay, it's a completely new signature. If I have a 3 terabyte hard drive and I run that entire hard drive, all the files, all the contents, through an MD5 hash algorithm, I'm going to get the same type of fingerprint in terms of the length, the number of characters and letters that I get here, and that uniquely represents that input. If I change one character on that hard drive, just one text file, one character, the signature will be completely different. So that's kind of why we call it like a fingerprint. It's a very unique signature, unique value that represents some input, no matter how large the size. Now we will get different size outputs based on the hash algorithm that we choose. So if I take this same, see, now we've changed this back to the original that I had, and notice we have A5 and 7B again. So the hash algorithm always produces the same output for the same input, but it'll produce a different length output and different contents based on our hashing algorithm. So if we change to SHA-1, we now have a longer fingerprint, longer signature, more characters and numbers than we did with MD5, and it's a completely different value. Okay, so D2 begins with D2, ends with 101. I change a single character, again the signature completely changes, right? If I change that back, right, I get the same value, right? So again, same input produces the same signature. Now if I only had this signature, I could not determine what this input is. right? There's no way to run this back through the hash algorithm. If I change this to SHA-256, I'm going to get an even longer signature. Now, without getting into too much detail, as you might guess, the longer the fingerprint output, the stronger the hash algorithm is. In other words, the less likely it is that that different input could produce the same output. Okay, that should never happen with a hash function, but it's possible with older, weaker hash functions like MD5. Theoretically, it's possible to get the same output with different input. Okay, it's extremely unlikely, but it's possible. So the stronger, the longer the signature, the stronger that the hash algorithm is. Just another use case I'd like to describe. So when you type your password into a website, what that website should be doing, and most do these days unless they're doing things insecurely, is they will take your password, your browser takes your password, sends that to the web server that's sitting on the internet, and that web server will take your password and run it through a hash algorithm, and then compare that hash value to what it has saved since your last login or when you registered. And if those values, these hash values, match, then the web server can determine that you know your password, right? And this is important because in the old days, and some sites today that still do things insecurely, they'll actually store your plain text password on the web server, all right, and then just compare plain text passwords. But it's much more secure to do it in terms of a hash signature, because if an attacker breached or compromised or attacked that website and was able to obtain all the registered users' hash values that represent their passwords, they wouldn't be able to determine what the plain text is from this signature. Because remember, a hash function is one way. You can't take the signature and run it back through the hash algorithm and get the plain text. But if the plain text is the same, you'll always get the same output, the same signature. So if I save that signature the first time you register on the website with your password, and then the next time you log in, run your password through that same hash algorithm and compare it to what you registered as a password, those signatures are going to match if you entered the same password or the same plain text. If your password is different, the hash signatures will be completely different, and the website can determine that your password is wrong without ever storing your plain text password. So that's a kind of a pro tip, if you will, but a best practice for saving password information on websites. Save it as a hash, or actually a salted hash, which is a little bit beyond the scope of our discussion today. All right, so during the competition, you're going to want to make note of this website. You will be asked to give the MD5, SHA-1, or SHA-256 hash of some input. And you can use online tools like this to very easily do that. Just copy and paste the input over here in terms of text, or browse to the file and then generate the hash. All right. Now let's go back to our presentation. Okay, so that's hash functions in a nutshell. What we're going to talk about next is we're going to talk about image metadata analysis. So every time we take a picture with our phone or any other device, there's metadata that is stored about that image. The latitude and longitude, where that file was, or where that image or picture was geographically taken, the date and time that the picture was taken, the type of device that was used, so on and so forth. And forensics investigators, security analysts use this metadata as part of their analysis, often when they are investigating crimes and data that are found on the devices, searching for evidence to support the criminal investigation that they're doing. So we're going to look at that in our next part. We'll see you then.